Today we have the first mini course and actually the first lecture on bootstrapping 2D loop models by Sylvain Ribault from IPHT Saclay. And please, Sylvain, take it away.
Thank you, Francesco, and I'm grateful to also to the organizers, Francesco and the Bootstrap collaboration, for this workshop in Complutense, which Francesco told me is, in fact, has nothing to do with computing. It's just the name of this place. So the subject of this lectures is the two-dimensional loop models. So these are models which we think are exactly solvable, exactly solvable conformal field series in 2 dimensions, although they are not solved yet. So I'll start with introduction, and then for today I'll review some necessary background in 2-dimensional CFT, but hopefully I will be able to derive the spectrums of these models. And then in the following lectures, we'll try to compute correlation functions using a mixture of analytic and numerical bootstrap methods. And after that, we'll compare what we get to the statistical definition of these models. So let me start by saying what these models are. So originally, you want to draw configurations of loops, of non-intersecting loops on some lattice. And use sum over all these configurations to get the partition function. Oops. So the partition function, Z, is the sum over loop configurations of some parameter n called the loop weight to the power the number of loops. And well, the loop weight is any complex number here. So with this type of model, you can reformulate well-known models like the ON model in any dimension, actually, or the POTS model, but only in 2D. Well, originally this ON model describes some vectors in an n-dimensional space, and the POTS model describes a discrete variable, a discrete variable in 1Q. So here it's a vector in R to the n, let's say. But with this reformulation, now the variables n and q will be able to take any complex values. Well, in fact, the n of the loop model is related to the q of the POTS model by n equals square root of q. And so special cases of these loop models include the Ising model, percolation, or polymers. And you can obtain these cases as limits from generic complex values of the parameter n. So then, well, these lattice models have critical limits. And in these limits, you obtain conformal field theories. And usually, these conformal field theories are not unitary, although they may have a unitary sub-theories. For example, the Ising model has a unitary sub-theory, which is the Ising minimal model, if you want. So, what do we know already on these models? Well, in the 1980s, the spectrums of conformal dimensions were derived using modular invariants. But now we want to rederive this spectrum in a simpler way, and also to compute correlation functions using bootstrap techniques. So let me say more precisely what methods we want to use. So a priori, we would want to do analytic bootstrap methods. And with analytic methods, you can, in fact, solve some two-dimensional CFTs. So you can solve, for example, minimal models or Liouville theory. So you may wonder if we can also solve loop models with the same techniques. Then we have to ask why does it work so well for these models? And the answer, I think, well, one answer is that in these models you have two independent degenerate fields. And here, what I call degenerate field is a primary field whose operator product with any other primary field involves only a finite number of primaries. So in Liouville theory and minimal models, you have two independent degenerate fields, and this is the key, as we'll see later, to solving these models analytically. So in loop models, we only have one degenerate field. And the resulting constraints are just not enough for solving the model. But, well, they are in fact enough, as I will show, for deriving the spectrum. And once we know the spectrum exactly, we can apply some variant of the numerical bootstrap, which does not require unitarity, and which gives us high precision results for correlation functions. And then from these numerical results, we can infer analytic formulas. So that's the idea. So what types of results do we get? Well, the main structural result on these two-dimensional loop models is that correlation functions are parameterized by so-called combinatorial maps. So a combinatorial map is just some diagram here. So let's say I have 4 vertices for a 4-point function, 4 vertices of valencies 3, 2, 2, 1. So I can draw some map respecting these valencies, like this map, for example. Well, the lines cannot intersect. I mean, that's from the definition of loop models. And the claim now is that, I mean, in fact, I can draw several possible maps. So another example with the same valencies would be this one. Well, in fact, you can, if you want connected maps, as an exercise, you can check there are 4 connected maps with the same valencies, 3, 2, 2, 1. So the claim is these maps are in one-to-one correspondence with a basis of solutions of crossing symmetry equations for some 4-point functions which correspond to this diagram. So let's say the set of combinatorial maps is in bijection with a basis of solutions of crossing symmetry. Okay. And then, well, we solve these crossing symmetry equations, we compute the corresponding structure constants, and then we try to guess analytic formulas for these structure constants. Okay, so that's the introduction. Are there any questions before we embark on the slightly more technical discussions?
Or what kind of lattice?
Well, it depends. It could be a square lattice, it could be a honeycomb lattice. It's really very model dependent and non-universal. But, well, these details usually are erased in the critical limit. Okay, so let's do some Carroll two-dimensional CFT So in particular, I want to construct the degenerate fields which play a critical role in analytically solving conformal field series in 2 dimensions. Well, before that, I mean, since you are not supposed to be very expert in 2-dimensional CFT. Well, I'm sure many of you know a lot about 2-dimensional CFT, but I think I need to do some quick reminders. For example, what is the Virasoro algebra? I mean, the algebra of conformal transformations in 2 dimensions. I'm just giving you the structure of the algebra because we need these commutation relations. So we have an infinite set of generators, Ln, and plus an identity generator, which commutes with everyone. And then the Ln, Lm are given by n minus m, Ln plus m, plus c over 12, n squared minus 1, delta n plus m, 0. So L0 is supposed to mean dilatations. So that's, if you want, our energy operator. So if we accept this describes the conformal algebra, then we have to look for the representations of this algebra. So which representations? Well, if we say that L0 is the energy, we want L0 to be bounded from below. And if we take a state with a minimum value of L0, this will turn out to be a primary state. So, oops. So a state which is eigenvector of L0 and which is killed by an infinite number of annihilation operators. On the other hand, if you act with some Ln, in fact, you decrease the conformal dimension by n, because L0 ln v is delta minus n ln v. Okay, so once we have a primary state, we can construct a representation by considering all the descendants of that state. So what are these descendants? Well, let's define a set of creation operators. So the product of the L minus Ni with N1 less than N2 less than Nk. So this set of creation operators is just 1, L minus 1, L minus 1 squared, L minus 2, etc. And then we define a Verma module, M delta, as the span of all these descendant states. So span of L V delta for L belonging to this curved L, the set of creation operators, assuming that all these descendant states are linearly independent. So that's the definition of the Verma module. Okay, so then is this Verma module irreducible? So the structural result is that it's irreducible if and only if there is no singular vector. And what is a singular vector? Well, singular vector is a primary state. Oops. V, which is not the same as the original V delta. So any state in the Verma module which is itself primary. So if you have a singular vector, then this singular vector generates with all its descendants a sub-representation. So our module is not, well, it's reducible. And then what you can do is to mod out this submodule to get some irreducible module. But before doing that, I want to remind you in which cases there exist singular vectors. Right, so I'm considering only Verma modules and their submodules. Well, if you want, in general, if the Verma module is reducible, it is also indecomposable. So if it has a submodule, if it has a null vector, you cannot decompose it as a direct sum of the submodule plus something else. However, if you're thinking about logarithmic CFT, I mean, a Verma module, by definition, in this Verma module, L0 is diagonalizable, so it will never be logarithmic, although it can be indecomposable. Okay, so are there singular vectors? So for example, we could look for a singular vector at level 1. Well, at level 1, there is only one state, which is L-1 V delta. And this state is a singular vector if and only if it is annihilated by L1. So what is L1 applied to L-1 V delta? Well, to compute that, you have to use the Virasoro commutation relation. So L1, L-1 is 2L0. And you have to remember that L1 annihilates V delta. So you just get 2 delta V delta. And therefore, L-1 V delta is a singular vector if and only if delta is 0, which means that the Verma module M0 is reducible. It has a submodule which is generated by this vector. Well, this thing has conformal dimension 1. So if you want, you have a M1 as a submodule of M0. So, I mean, you can do this calculation by hand for the first few levels. I mean, what I call level is the total mod number of my creation operator, right? So you can do this for the first few levels, but you will have results for at any level on the existence of null vectors. So, but to write these results, I mean, So usually this special dimension where you have null vector, I mean, here it's very simple, it's 0, but in general it depends on the central charge. And to have a simple formula, we need some different notations. So C, the central charge, which appeared in the Virasoro commutation relation, let's write it as 1 minus 6 beta minus 1 squared. And let's rewrite the conformal dimension as C minus 1 over 24 plus P squared. And then the theorem is that the Verma module M delta has a null vector at level R times S if P is of the type PRS, where PRS is defined as 1/2 beta R minus beta minus 1S. So this null vector at level Rs, if you want, we can write it as L minus 1 to the power R times S plus some other creation operators of the same level applied to the V delta Rs. And then M delta Rs is reducible. And it has an irreducible coset, which is M delta Rs divided by, well, the submodule M delta Rs plus Rs. So that's irreducible coset. Okay, any questions on that? So I promise we'll soon stop doing this type of algebra, but it's important because this is what leads to degenerate fields. Well, we are not yet doing fields, but we will soon consider fields. So now let's consider some irreducible coset like that, what does it mean? Right, so you're right, there could be several null vectors. However, in general, it doesn't happen because this delta RS, or this PRS, if you want, is a function of the central charge via this parameter beta. So if you want to have two null vectors in the same Verma module, you need delta R1 S1 equals delta R2 S2. You need an equation like that, and this implies that, well, your central charge will take some specific value. Right, that's what happened in Minimal's model, but does not happen generically. So indeed here I was talking about the generic central charge. And in minimal models, your irreducible representations are much more complicated. You cannot just divide by one sub-Verma module. But yeah, we don't need to study this in detail. Okay, so this formula is very important and very simple at the same time. So the momentum, I mean, this P is called the momentum. This is what I call a degenerate momentum, corresponding to a degenerate representation. So, well, what I call a degenerate representation is, in fact, this irreducible coset. And what happens when you have a degenerate representation? Well, if you consider the primary state of that representation, V delta Rs, so we already know it's primary, so it's killed by ln positive, and it's eigenvector of L0, of course. But in addition, well, it has a vanishing singular vector. So we have some singular vector, which I could call LRS. So that's a creation operator acting on this V delta RS is 0. So I want to change notation for this operator to really indicate that it's not just a primary field with this dimension, but that it belongs to an irreducible coset. And so I'm calling it VDRS, D for degenerate. I'm calling that a degenerate state. So for example, if you remember this example at level 1, so for delta equals 0, we had L minus 1 V0, so that was our singular vector. But we set it to 0. That's the meaning of taking the coset. So in the new notations, we are just stating that L minus 1 V D11 is 0. And similarly, if you look at level 2, you have L minus 1 squared plus beta squared L minus 2 V D21 is 0. So that would be our degenerate state with a vanishing null vector at level 2. So this extra equation, I mean, if you want the null vector equation, will be really the key to the properties of the degenerate fields. But to reach that, I have to upgrade my state into fields using the state field correspondence. So that's what we are going to do now.
There exist examples where the operator for the singular vector in the representation can have non-zero correlation function with other operators. Here, you are imposing that the singular vector vanishes. So is it derivable from some lattice?
No. It's really an assumption that the null vector vanishes. And indeed, you can have non-vanishing singular vectors.
OK.
It happens in Liouville theory with C less than 1, for example. Well, it has confused people for some time, but it happens.
OK, thanks.
Okay, so we want to transform all our vectors now into fields. So how do we do that? Well, we just take a vector and we add a dependence on z, where z lives on the Riemann sphere, and we call it a field. Well, okay, so for the moment it looks very trivial, but the axiom which tells you how v depends on z is that the derivative of z of v with respect to z is just L minus 1 v of z. So now it becomes a rather non-trivial construction. So, and this axiom is really supposed to apply to all fields. In particular, it's supposed to apply, I mean, if you start from a field, now you can take its descendants, or you can act with any Virasoro generator. Well, let me write this, I mean, alternatively as ln at z, v of z. I mean, you should think of the Virasoro algebra as acting on each point, z. And then if you apply this axiom to these fields for any n, you'll get, well, the following results. So let me define the linear combination of all these generators, ln z, over y, oops, y minus z to the n plus 2. Well, as a consequence of this axiom, we have that d by dz t of y is 0. So this t of y, in fact, does not depend on z. And so this t of y we call the energy momentum tensor. So T of y is a very convenient object. For example, we can characterize a primary field by its operator product expansion with T of y. Well, ln z is a Virasoro generator at point z. So no, we had one Virasoro algebra when we were just doing, well, algebra. Now that we want to do field theory, we have an action of the Virasoro algebra at each point of our space.
Well, what kind of object is ln z? Is this an operator which acts on some vector space, or is this a differential operator? Like, what is it? I mean, you wrote the symbol ln of z. I'm just not understanding what kind of mathematical object is this thing.
Right. So,
like,
it's well, if you want, it's a kind of bundle of your Riemann sphere, which takes value in the Virasoro algebra. But the point is that when you deform your, well, when you move your point, you have a non-trivial linear transformation of the Virasoro algebra from one point to the next, which is in fact determined by this axiom.
well, but in this axiom you have L minus 1, which doesn't have this argument z.
Well, it should, in fact. But for L minus 1, it's a bit trivial. Well, in fact, yeah, L minus 1 itself doesn't depend on z. Yeah, it's two notations for the same thing. So when I write ln v of z, it's implicit that this ln is the ln at point z. When I want to emphasize that it depends on z, I write it explicitly. But I want to... It's a notation.
Okay.
It's a notation which I need just basically for this particular formula, where I want to remind you that ln depends on z.
But when you say it depends on z, can I compare it like at z equals 1 and z equals 2 and say that they're different?
Yeah, in principle you can. I mean, I expect it's a bit complicated, but in principle here you have the connection for this bundle, basically, so you can use that to transport your Virasoro algebra from one point to the next.
So what is the bundle? Is this the bundle of Fermat modules?
Not quite. I mean, the Fermat modules are the representations of that, but now we have a bundle of algebras.
Well, where does V of Z live?
So V of Z lives in the bundle of Fermat modules.
Okay. All right, thank you. That makes sense.
Okay, so thank you for the questions, which, allowed me to give some hopefully useful clarifications. So now this T of Y, so I want to state that it's very convenient, for example, to state that the field is primary. You just have to compute T of Y V delta of Z. So by definition of T of Y, it's just the sum of all these terms. So sum for an integer ln V delta of Z over Y minus Zn plus 2. But now if you remember the definition of primary field, it has to be killed by all terms with positive n. So the first non-zero term is L0 V delta, but L0 V delta is delta V delta. So we have delta over Y minus Z squared V delta of Z. Next term is L minus 1. L minus 1 by this axiom is the derivative. So we have d V delta of Z plus Y minus Z. And all the other terms are non-singular. So basically this OPE is now equivalent to the statement that V delta is a primary field of dimension delta. And more generally, this T, this energy momentum tensor, and its operator product expansions will allow us to encode the action of conformal symmetry and to derive conformal word identities. Okay, so let me then remind you some basic axioms of CFT, which are true in 2D like in any other dimension. So we assume there exists an operator product expansion. So for any two fields, not necessarily primary, we can expand this product of fields over a basis of fields at Z2, let's say. So we have a OP structure constant C, OP coefficient, C12K of Z1, Z2, so that's a number, and Vk. So K here runs over a basis of fields. And this operator product expansion is supposed to converge on some finite domain of Z1 around Z2. And moreover, it's supposed to be commutative. V1, Z1, V2, Z2 equals V2, Z2, V1, Z1. So these are really the usual axioms. But now we have to see what happens specifically in 2D and how the conformal symmetry constrains this operator product expansion, and in particular the coefficients. So I won't do the derivation in detail, but the idea is that you use associativity of T, V1, V2. And this puts strong constraints on this CK. In particular, it completely determines the dependence on Z1 and Z2. And you end up with the following OPE. So for simplicity, I'm writing it for primary fields now. V delta 1 Z1, V delta 2 Z2. That's a sum K C1 to K, Z12 to the delta K minus delta 1 minus delta 2 times V K of Z2 plus a sum over descendants, well, descendants except the original primary, of Z12 to the power L, some coefficient F delta KL delta 1 delta 2, L V delta K, well, L VK, sorry, L VK of Z2. So let me unpack a bit this formula. So now the idea is that not only we determine the z dependence on this coefficient c, so the d dependence is present here and there, but also we determine the contributions of all descendants from the contributions of the corresponding primaries. So the sum now is only over primaries. So we have numbers which are, the only thing which is not determined by this conformal symmetry is this number here called the OPE structure constant. So now we have the primary and the sum of the descendants. So here L is the level. So for example, L minus 1 squared is 2. That's level 2. And then this coefficient F is known. It's completely determined by conformal symmetry. And this LVK here is just some arbitrary descendant of this VK. And all this is just a consequence of this associativity of T V1, V2. Okay, and finally, we are reaching our goal, which is to understand the OPEs of degenerate fields now. Because I introduced in my introduction degenerate fields as fields whose OPEs contain a finite number of terms. So now I'm going to claim that this is also a consequence of the associativity of TV1, V2. Well, in fact, we can see it in the simplest example. So if we take, for example, VD11, well, VD11 is a field which is killed by L minus 1. So L minus 1 VD11 is 0, but this is also D by DZ1. So let's say my field V1 now is VD11. Okay, so this is 0. Oops. So now if I assume my field V1 is this field here, and I want, I take a derivative with respect to Z1, well, I just have to look at the first term in this OPE at the primary. I want basically this quantity to be independent from Z1. So remember that delta 1 is 0 for this particular degenerate field. So I just have d by dz1, z12 to the delta k minus delta 2 is 0, which is equivalent to delta k equals delta 2. And therefore, from the vanishing null vector here, we obtain the fusion rules of this degenerate primary field. And the fusion rule is that VD11 V delta, well, gives you only one primary field, V delta itself. So that's the simplest case of a degenerate fusion rule. Okay, now let me write the next cases. I'm not doing the derivation, although you could do it again using well, associativity of OPEs. So the next cases are VD21. So VD21, if I remind you, is killed by L minus 2 plus beta squared. No, sorry. It's killed by L minus 1 squared plus beta squared L minus 2. Okay, so now L minus 1 squared is a second order derivative. So in fact, if you do an OPE, you'll find two terms, two possible primaries. So it's simpler to use the P notation, the momentum, rather than a conformal dimension, because now these two terms are just Vp plus or minus beta over 2. And at level 2, you have another degenerate field called VD12. And its OPs, again, contain two terms like that. So, okay, so I have derived these OPs. Well, derived maybe is an exaggeration, but at least try to justify and to give you a hint of how to derive them. in fact, there is an approach to 2D CFT which is based on categories, and where you would basically start by assuming such OPs, so assuming some kind of category of modules, some fusion category, and then try to derive all the rest. Okay, and then, I mean, I'm not doing level 3, etc., because we don't need to. We can deduce that by associativity. So that's what we'll do next. But other questions up to now? Okay, so, oops. So if we have no questions, so from these basic OPs, we'll try to derive, well, minimal models to begin with. So to do that, we have just to use systematically OP associativity. And the first implication of associativity is that the OP of degenerate fields gives you only degenerate fields. Because a degenerate field is a field whose OP is finite, if you want, meaning it contains finitely many primaries, but by associativity, this property is conserved. And then, moreover, you can in fact compute the OPs of degenerate fields, starting from the ones we know, VD12, VD21. So for example, if you compute the OP of VD21 with itself, you'll find two fields according to this formula. And these two fields, you find that they have dimensions P11 and P31. And moreover, you know from the first line that they have to be degenerate. So therefore, you say they are just VD11 plus VD31. And you can go on like that. So what do you find? You find that VD21, VDRS is the sum VD R plus minus 1, oops, R plus minus 1 S, and VD12, VDRS okay, and then you can even compute the OPE of two arbitrary primary fields, VDR1S1, VDR2S2, and you find a sum from R1 minus R2 plus 1. The sum runs by increments of 2. Same for S. VDRS. So we have this algebra, if you want, of degenerate fields. And now we can start to build models, like minimal models. So let me define a minimal model as a CFT whose spectrum of primary fields is finite. So we want finitely many primary fields. So of course we want to use degenerate fields, because this guarantees us that by taking OPs we get only finitely many terms. But is it enough to take degenerate fields? Maybe not. I mean, if you start from a non-trivial degenerate field like VD21, and you do repeated OPs with itself, then you're going to generate infinitely many degenerate fields. So you're not getting a minimal model. So to really get a minimal model, you have to go a bit further and to follow the suggestion we had before, so to take fields which are multiply degenerate. So a field which obeys several null vector equations. So we can start in an example by taking this field VD21 And let's assume that it's the same as VD22, which means that it has a vanishing null vector at level 2, but also vanishing null vector at level 4. So let's call this field sigma. So first, the coincidence of these two fields gives us a constraint on the central charge. So the dimensions of these two fields must be equal. And in fact, this implies that the sum of the corresponding momentums is 0. Well, just because the difference cannot be 0. And what is the sum of these momentums? So if you remember the definition of PRS, well, this is 1/2 4R minus, 4 beta minus 3 beta minus 1. So beta squared equals 3/4. Central charge is 1/2. Well, beta squared was a notation for the central charge. So let me remind you that C was 1 minus 6 beta minus 1 squared. Okay, so this field can exist only at central charge 1/2. And now we can start computing its OPEs. So if we compute sigma sigma, well, nothing special happens. We just get VD31 plus VD11. So let's call this epsilon, and let's call this 1. So then we can compute, for example, epsilon epsilon. But the thing is, epsilon epsilon, I mean, usually you would expect 3 terms according to these generic fusion rules, but epsilon is multiply degenerate itself, just like sigma. In fact, this epsilon is not only V31, but it's also the same as V12. And if you want to respect the fusion rules of both of these fields, you'll find that epsilon epsilon is identity. And you can also compute epsilon sigma equals sigma. And so what you get is in fact the Ising minimal model. And indeed it's a minimal model because it has only finitely many fields, well, 3 primary fields in fact. Okay, well, you might be a bit worried that we don't have the energy momentum tensor in the sigma sigma OPE, for example. But the point is, oops, what's happening? Yeah. In 2 dimensions, the energy momentum tensor is a descendant of the identity. It's L-2 acting on the identity. So here I'm writing only Virasoro primary field, so that's why I don't write the energy momentum tensor. Okay, so from these fusion rules, we can derive this Ising minimal model, and in fact, we can derive all the other minimal models. So let me quickly remind you how this works. So we take, for any P and Q here, we take a beta squared equals P over Q. Well, P and Q are coprime. And then we defined the spectrum of primary fields as the fields VDRS, which is the same as, in fact, V P minus R Q minus S for R and S in this interval, 0P times 0Q, but also R and S strictly positive integers. So this gives us a finite set of primary fields called the Katz table. And the claim is that if you do OPs of these primary fields with each other, as a consequence of the fusion rules of degenerate fields, you stay always in the Katz table. So you will indeed get a minimal model. But the central charge has to be rational, because beta squared is rational. And now from this, we can derive Liouville theory. Well, maybe that's not the usual or original way to derive Liouville theory, but the point is that we have here beta squared, which is any rational number. So rational numbers are dense in real numbers. So what we can do is to take beta squared, go to beta 0 squared. So beta 0 squared, any real positive number. So what happens if we take this limit? Well, anyone has an idea? I mean, first we have to look what happens to the Katz table. So if we want to get to an irrational beta 0 squared, we have to send P and Q to infinity, both of them. So the Katz table will become very large, infinitely large. And what happens to these degenerate fields? Well, now it depends what we are doing to the indices, to the Katz indices R and S, when we are sending beta squared to beta 0 squared. Because we could take this limit as at fixed R and S. And then the only thing that would happen is that we get S, which is made of all degenerate fields. So with any integer values for the indices R and S. So this I want to call a generalized minimal model. So it's no longer really a minimal model because its spectrum is now infinite, but it's discrete infinite. So that's one possibility. But there is another possibility, assuming beta 0 squared is irrational. So remember, well, I told you this was an important formula. Well, that's why I'm writing it all the time. So what is PRS, the momentum of this degenerate field? So it's 1/2 beta R minus beta minus 1S. And what happens to these momentums when we take the limit? Well, all these are real numbers. So we are on the real line. Here we have beta. And the important thing is that beta minus 1 here, well, minus beta minus 1, if you want, goes in the opposite direction. And then we take arbitrary combinations with a positive integer R and S. And PRS become dense in this real line. So therefore, we could arrange for PRS to go to any P0, any real P0. And then we would get a spectrum, which is now integral dp0 over real numbers of what? Well, sorry, I'm writing the spectrum as just a set now, so it's just the set of vp0 for p0 belong to R. So the fields I'm getting in the limit are no longer degenerate because basically the null vectors go away to infinity, to infinite level when I take the limit. R and S go to infinity when I want to reach some arbitrary P0. So I get a continuous spectrum. So I want to call that the spectrum of Liouville theory. And I can also compute the operator product expansions in Liouville theory by taking the same limit. So by taking the limit of these OPEs of degenerate fields, I can get, well, the OPE in Liouville theory, VP1, VP2, and you'll get simply an integral dp VP. Okay, so this does not yet prove that Liouville theory exists. Well, or at least to know that we would first have to prove that minimal models exist in the sense that they are, well, satisfy all the axioms. So for the moment, I'm just deriving the spectrum. But this is, well, one way to get Liouville theory. Although only for specific values of the central charge, namely, I mean, this beta now is real positive, which means that the central charge is less than 1. So here we get Liouville theory with a central charge less than 1. But we could guess, and this would be true, that Liouville theory in fact exists for any value of the central charge, any complex value of the central charge, with the same spectrum and the same operator product expansion. Okay, so this was part 2 about Carroll CFT. So now we'll suddenly remember that in fact the conformal algebra is made of left-moving Virasoro algebra and a right-moving Virasoro algebra, so we'll have to do non-Carroll CFT. But before that, are there questions? Yes. Yes, essentially the limit gives you a specific measure. But it's in fact the flat measure which I wrote there. I mean, this is true at the level, if you want, of 4-point functions, for example. This is the measure that appears when you decompose a 4-point function into conformal blocks. Right, so that's a subtle point. So what I'm calling here Liouville theory with C less than 1 is what is called in the literature time-like Liouville theory. I just don't want to call it time-like because the spectrum is always space-like, whatever the central charge. The spectrum is the same. Well, for C less than 1, yes. But now, indeed, I'll comment more on this when we reach correlation functions, but indeed there is you don't get generic central charge from C less than 1 by analytic continuation. Well, at this level, nothing happens, right? At this level, it looks like it's the same, but at the level of 4-point functions, you have singularities and you can't do the analytic continuation. And even at the level of 3-point functions, you can't do it either. Okay, so let's move to non-Carroll conformal field theory. So, in fact, the conformal algebra in 2 dimensions is Virasoro times Virasoro bar. So left-moving Virasoro algebra times right-moving Virasoro algebra. And what's the difference between these 2 algebras? Well, if you remember, the left-moving acts on fields by d by dz v of z equals L minus 1 v of z. But now if you... The right-moving algebra determines the dependence on the derivative with respect to z bar. So d by d bar v of z is L minus 1 bar v of z. So the Virasoro bar has a set of generators ln bar. And so since we have these 2 algebras, 2 commuting algebras, our primary fields now, well, they have both a left and a right conformal dimension. And the difference between these 2 dimensions is called the conformal spin. So let me... Okay. So, let me remind you what are the 2 and 3-point functions in conformal field theory now. I mean, these are completely fixed by conformal symmetry, so I won't do the derivation, but the result is that V delta 1 of Z1, no, sorry, not V delta 1. Now it has a delta 1 and a delta 1 bar. So for simplicity, let me write it as V1 Z1, V2 Z2, but assuming both are primary, well, this is some structure constant B1 2 times delta 1 delta 2. So the dimensions have to be equal on the left and on the right. Z1 2 to the minus 2 delta 1 modulus squared. So by modulus squared now I mean something slightly strange. So by f, for some function of conformal dimensions and of position z, for me the modulus squared is f of delta z times f of delta, delta bar z bar. But here z bar is really the complex conjugate of z, whereas delta bar is independent from delta. So that's, I will use this notation all the time, but that's, so beware. I mean, this is slightly tricky. So here I'm taking the modulus squared of this expression. So here it means that I'm really enforcing that delta 1 equals delta 2 and delta 1 bar equals delta 2 bar. And for the dependence on z, I'm just taking a product of z12 and to some power and z bar 12 to some other power. So this is the 2-point function, and b12 is the 2-point structure constant. And then, well, we have a 3-point function, which probably you've already seen. So v1, z1, v2, z2, v3, z3 equals some 3-point structure constant c1, 2, 3, and then the modulus squared of a big expression, z12 delta 3 minus delta 1 minus delta 2, z2, 3, z3, 1, delta 2, 3 modulus squared. So now the non-trivial thing is to assume that these correlation functions are single-valued. I mean, because when I'm writing some z to some power, I mean, if the power is not integer, I can have trouble with single-valuedness. So by single-valued, I mean that when I do some zi goes to e, well, let's say, no, z1, zij goes to e to the 2 pi I zij, I want my 3-point function to stay the same. And in fact, this gives me a constraint on conformal spins. Because here I have something like z12 to some power, so some delta. I have a z12 bar to some delta bar. But what matters for single-valuedness is the power of z12 over z12 bar, which is essentially delta minus delta bar. So it's a difference of dimensions, of left and right dimensions, so it depends on spins. And single-valuedness of this correlation function, of 2- and 3-point functions, imply that spins Si are half integer, and they are conserved modulo integers. Okay, so this constraint on spins will be very fundamental for deriving the spectrum of loop models, basically. So in addition to the fusion of degenerate fields, basically this is what we need to derive these spectrums. Okay, now maybe a few technical notes on this structure constants. So we have the 2-point structure constant, if you remember, was b12, or let's say bij. But we can assume that bij is of the type bi delta ij. So in a sense, we can diagonalize the 2-point functions such that only the same fields have non-vanishing 2-point functions. And if you do that, then you can relate the 3-point function Cijk to the OP coefficient we had before, which was Cl, let's say ij b. Oops. No, sorry. Oops. Now you can always relate the OP coefficient with a 3-point function, but now it becomes very simple. It becomes just Cijk bk. And also you can relate this b to the c because if you assume that it's an identity field, then of course if you have a 3-point function with an identity field, it becomes a 2-point function. So you get that Cijj is bj. The only thing I don't want to do is to get rid altogether of this B, which is often done in rational CFTs. I mean, you can always renormalize your fields such that this B is 1. But if I'm doing that, let's say in Liouville theory, I will get 3-point structure constants that are not analytic. Because to do that, I need some to introduce some square root of B if you want to get rid of B. And that we don't want to do. So we have to keep this B. Okay, so after these reminders, I think we can try to derive the spectrums of loop models based on a few simple axioms. So any questions until now? Okay. So first, let me just enumerate which type of fields we can admit in the spectrum. So we'll start with the degenerate fields of the type VDRS. So that's the notation. Here the variables are just strictly positive integers. And the conformal dimensions, left and right, well, the momentums left and right are just the same. So here, I'm considering degenerate fields that are degenerate on the left and on the right with the same dimension on the left and on the right. Okay, so then I want to consider also diagonal fields. So let me write that as VP for any complex momentum. Diagonal means the same momentum on the left and on the right. And then the non-trivial part is really the non-diagonal fields. Yeah, here for the moment the central charge is just any complex number. But we'll soon derive a constraint on the central charge, in fact. So non-diagonal fields, well, I could parameterize them by their left and right dimensions, but it turns out it's more convenient to parameterize them in terms of Katz indices R and S, such that the left dimension is delta RS, and the right dimension is delta R minus S. And then these numbers for the moment are just arbitrary complex numbers. They are just another parametrization of the left and right dimensions. And if I do that, I mean, this non-diagonal field has a conformal spin, which is delta R minus S minus delta RS. So that's R times S. That's the conformal spin, if you want, of this non-diagonal field. So V, for the moment, is a primary field with these conformal dimensions. Yeah, the notation is a bit similar, but it's different because here we have different left and right dimensions, plus here we assume R and S are integer. No, for R and S for the moment are just arbitrary, and the dimensions are different. Okay, so now we want some conformal field theory, which is built from fields of this type, primary fields of this type. And then let's make a few more axioms. So we assume that, yes? Sorry.
So why for the degenerate fields you assume that it's the same R and S for
why do
DNP bar?
degenerate fields? Well, that's axiom if you want. I mean, I could try to consider degenerate fields with different R and S. However, typically they would have a spin which would not be half integer. So at generic central charge, I can't really do that.
So you cannot do this generic central charge, is this statement?
Right. Unless I violate my condition that the spin is half integer.
Okay. All right. Thank you.
So here the RS are the same on left and right. Here it's just a notation to say that the dimensions are like that. No, the main difference between degenerate and non-diagonal is this thing. Here, this delta R minus S is not the same as delta RS. Diagonal and degenerate. Yes. The difference is that this P takes special values parameterized by integers. And this P here is just a complex number. Okay, so let's assume that central charge is generic. Which means for us beta squared is not rational. And I want also to assume that conformal spins are half integer, which was a consequence of single valuedness. And so that means R times S for non-diagonal fields is a half integer. And then the last assumption is that there exist degenerate fields. But we have to study slightly more in more detail what are the OPs between degenerate fields and these fields. So let's see how much time. Oops. Yeah. So I think we have time to derive these OPs, but maybe not yet. Maybe we don't have time for the spectrum itself of loop models. So what's the OP of a degenerate field? Let's say V21 with a diagonal field Vp. Well, we already computed this OP in the context of chiral CFT, where we had only one Virasoro algebra, and we found some Vp plus or minus beta over 2. But now we have a left and right Virasoro algebra, so left and right dimensions, which are not necessarily the same. So in principle, we could in fact get 4 terms. We could get some fields with left dimensions p plus minus beta over 2, and right dimensions also p plus minus beta over 2, right? And these two signs in principle could be different. However, we still want the spin of this thing to be half integer. So we want the difference between the left and right dimensions to be half integer. And generically, this means that you have to take the two signs here to be the same. And therefore, we are back to this formula, except that we now interpret it as OP of this degenerate field with a diagonal field, and you only get diagonal fields. So then for non-diagonal fields, what is VD21 VRS? Well, again, yeah, here the axiom which leads to this result is that the spin is half integer. If you accepted the 4 terms, some of them would have non-integer spins, so non-half integer spins, so we throw them out. So we'll do the same for non-diagonal fields. So in principle, we get 4 terms, just because both on the left and on the right, we have 2 terms each. And these 4 terms, well, that's where it's nice to use these indices R and S to write non-diagonal fields, because these 4 terms are written as V R plus or minus 1S plus V R S plus or minus beta squared. Sorry, you say you could compute this and you don't need an axiom to derive the... Well, I'm not in a constructive approach, right? In the Bootstrap approach, we only have axioms. There is no construction of this thing out of a path integral, for example. Okay, so for a non-diagonal field, I also have 4 possible terms. And again, I have to look whether these terms have half-integer spins to know if I can keep all of them at the same time. And so what are the spins here? So I have to compute the differences in spin. So I will assume that this VRS has integer spin. Yeah. Which second term? This one? Well, for the moment, it's not yet excluded. I will want to exclude it because the spin will turn out to be non-integer, but I have to show it. I mean, of course, the notation suggests that the good term is this one, but in fact, I could also eliminate this term and keep this one if I wanted. It will be a choice, one or the other. So to see that, you have to compute such spin differences, like S R plus or minus 1 S minus S R S. But the spin, let me remind you, is just R times S. So this is just basically plus or minus S. And so you also have the spin differences S R S plus or minus beta squared minus S R S. And this is just plus or minus R beta squared. So you want all this to be, so RS, you want S, and you want R beta squared to be half integer. And moreover, we wanted beta squared to be irrational. So there is a contradiction here. We cannot have all these things half integer and beta squared at the same time irrational. So we have to remove something. And the thing we want to remove is this one. So let's remove this term, and then we are happy. We find an OPE where everyone has half integer spins. But at the same time, we find a very important condition, which is that S has to be half integer. And so maybe to conclude for today, we have derived OPEs for between non-diagonal fields and degenerate fields. So let me write them here. So VD21 VRS is sum VR plus minus 1S. VD12 VRS similarly is just sum VRS plus minus 1. And that is what from this we will derive the spectrums of loop models. Okay, thank you.
Any urgent question?
Sorry, maybe you will justify this a bit later, but this looks a bit arbitrary. You started with a strange answer. You told us there's degenerate, there's diagonal, and then you derive by self-consistency these conditions. But where does this all come from? Maybe this will come clear later.
No, well, I don't think it's arbitrary. I mean, fundamentally, I'm just using very natural assumptions about basically spins being half integer, which follows directly from a single valuedness. So
no, but the original list that you started with, this
the original list indeed. I mean, what can look arbitrary is the parametrization of non-diagonal fields by Katz indices. But that's just because I have the benefit of hindsight. So we did already originally this type of calculations with by parametrizing well naively the non-diagonal fields, and it was a bit messy. And later we found that the more efficient way to parameterize non-diagonal field like that, it just makes the calculations nicer, but it doesn't change the argument at all. It's just the same result, that these are the OPs of, if you want...
But I guess the broader question, why should I mean, presumably this comes from many years of working with the concrete models, but why should I believe that there is such a theory with this diagonal and then, I don't know, it just looks very magical.
So you can think of minimal models. I mean, there is a classification of minimal models. You have diagonal minimal models, and then you have non-diagonal minimal models. And the basic motivation is to look at the same thing as generic central charge. So generic central charge, you already know Liouville theory, which is diagonal. And then the natural question is, can you find non-diagonal CFTs that are tractable, let's say? And tractable means, in fact, that you want degenerate fields to exist. Otherwise, there is little you can do in the analytic bootstrap. And so from this, you are incited to look at OPs of degenerate fields with non-diagonal fields. So that's just what I'm doing now.
Thank you.
Sorry, so you say in Liouville theory?
The degenerate fields are just a specialization of the diagonal fields or by any continuation with back to P. Is the point here that your degenerate fields are not related to the VP by any kind of analytic continuation in P?
Well, that's another subtle question. So in Liouville theory, indeed, you may wonder, well, in Liouville or in any CFT, in fact, whether the limit of some diagonal field when P becomes one of these discrete momentums, so is it the same as the degenerate field? And, well, there are several viewpoints on the question. So if you start, for example, from construction of the Liouville path integral, the answer is basically yes. So it's easy to see in the case of the identity field, which becomes just one when you take the limit. However, from the point of view of the bootstrap, there is no reason why this should be true. I mean, you take the limit of a Verma module, it could very well remain a Verma module in this limit. And the answer to this question really depends on the correlation functions. You have to look at the analytic properties of three-point structure constants to answer this question. So you answer it in the context of some correlation function. And the answer in Liouville theory is that this is yes if C is any complex number but not in this half line, and no if C is in this half line.
But in the model you're now describing, is there such a relation between the VP and the degenerate fields?
In the loop models, well, in fact, we have not really thought about this question, but I think the answer is no.
Thank you.
Maybe a final question. Okay, if not, let's thank Sylvain again